Hi everyone. Today I'm gonna talk about this project that I've been working on together with Sushruth Thorat and Tim Kitzman about category-orthogonal object feature guide modulatory operations in recurrent neural networks trained for invariant object categorization, which is a mouthful, but I will explain what it means shortly. So, role of recurrence in neural networks. So everyone knows that recurrent connections are prevalent in biological brains, but what are recurrent connections good for? So one thing that recurrence enables you to do in computational terms is to perform conditional operations. So for example, in language, based on the context of a previous word, for example, a negation, you can interpret the meaning of another word differently. Or in vision, you can interpret an ambiguous local image region as an edge or as noise based on the global shape context. And artificial recurrent neural networks have been shown to have a performance advantage also in object categorization, especially in conditions of noise and clutter in the image. So to see this in terms of conditional contextual operations, what are the conditional operations involved in this categorization task? So an image such as this very artificial one on the right is not just a function of the object category, but it's also a function of category-independent auxiliary variables, for example, of location. So in, for example, here in this image, there's a true object category, which is the number 5, and there's a true object position, which is the left. And there's a bunch of clutter or debris that resembles the target objects and needs to be separated from it. So one strategy, one way to deal with this task is if you take the image as input and you process it through a feed-forward pass of a network, what you obtain is evidence for different visual categories, which can be in different locations. So this can be seen as a joint distribution of category and location. The gray here indicates the amount of evidence for an object being there, basically. And based on this noisy picture, so you have something that looks kind of like a 5, something that looks kind of like a 1, have something on the right, something on the left. Based on this, you can use the auxiliary variable to narrow down your search space in a way. So you filter only the location of interest. And in this way, you can see it as sharpening the distribution and narrowing it down to a specific category and a specific location. Then you can send that information through feedback in such a way as to filter the relevant information from the input or from the previous layers. And then feed forward that information back again, so you can do this filtering in a iterative way. So to find out whether this strategy is something that happens in recurrent neural networks performing categorization, we designed a data set which comprises different object categories and different auxiliary variables. So the auxiliary variables are position, X and Y, rotation, and scale. So as you can see, at the leftmost column, you have the original image, and then it's the digit, which is on the top left in the original image, can be shifted in horizontal position or in vertical position, or it can be rotated, or it can be scaled. And in addition to the target object, there's also debris all around it, which looks like the target objects because it's made of fragments from other objects in the data set. So that makes it a challenging task because the network has to separate the true object from the debris. So each auxiliary variable has two possible values with a little bit of jitter. There are 20 possible object categories, which are objects drawn from the MNIST data set of handwritten digits and from the fashion MNIST task of clothing. So the task is 20-way classification. So the architecture that we used is looks like this. So it's a pretty standard convolutional neural network with two convolutional layers and a fully connected layer. And it has both top-down and lateral connections. So top-down are recurrent connections from one layer to all the layers below it, including the input. We also enable to manipulate the images directly. And lateral connections are connections from a layer to itself in time, the standard recurrent connections. This is run for 4 time steps. This is fixed. And then the final layer is a fully connected layer, FC2, which gets input from all of the time steps of the network concatenated and can do whatever it wants with it. So it can weight it in any way it wants. This was to not create any sort of bias that it had to accumulate information over time, or it can do whatever it wants, basically, across those 4 time steps. And the way the recurrent and the feed-forward information are combined looks like this. So you have your standard input multiplied by weight, either linear or convolutional layer with bias. Then it goes through a ReLU nonlinearity, so 0 for anything 0 and below, equal to the input for anything above. And then it's multiplied by a gain term, which is the outcome of the recurrent computations. So you have your feed-forward vector, which has gone through the ReLU nonlinearity, and it's multiplied element-wise with the recurrent connection, with the recurrent information. So this is a bit different maybe than what a lot of people do, which is to sum the recurrent and feed-forward vectors together. We also did it with summing, and the results are consistent, but we chose to stick with this version. So test accuracy, it's 82% on the test data set, which is 10,000 images. The baseline being 20-way classification is 5%. So we know that the network can successfully solve this task. And so we now look at what strategies it's using to do so. So is it using information about the auxiliary variables? So we looked at auxiliary variable information across time. So this is measured as the accuracy of a linear classifier, in this case an SVM, on the layer's activation for each moment in time, each of the 4 time steps. And the classification is 2-way for the auxiliary variables and 20-way for category. And this is what we get. So you can see the 4 category and the 3 auxiliary variables and the 4 layers of the network. So you can see that the information about both category and auxiliary variables keeps increasing across time at all layers. This is the average across layers, which is, as you can see, is increasing. So this is so this was about the information contained in the layers activations. What about the information contained in the actual recurrent information flow? So this time the classification is performed on the recurrent information, which is what gets combined with the feed-forward activations. And it's the combined product of all the top-down and lateral connections for that layer. And this is what we get. So also in the recurrent flow, we see that information about category and auxiliary variables keeps increasing across time. Here there are 3 time steps because, of course, there's no recurrent information the first time step. Yeah, and this is true from for every layers from the input to the other 3 layers. So does this information, is it a pure epiphenomenon? Because if information is in the feed-forward layers and you project it randomly, it will look like this? Or does it play any functional role in the task, in classification? So we looked at the functional relevance of recurrent information using a perturbation approach. So what did we do? So for example, we take an image and we perturb the y, the vertical location. So this is the original image, which gets sent through the network from one layer to the other. It does this, sends the recurrent information forward in time. And then we take a manipulated version. So in this case, it's perturbed in the vertical location of the object, which is a suitcase. We get the recurrent activation and we feed that instead of the true activation to the network. So the network is getting the information it would have gotten if the auxiliary variable had a different value, and we don't give it the real information. So it seems to be stuck. My slides are okay. Wait. Oh wait. Yes. Okay. So this corresponds basically in feedback parameter space. So if you see the feedback vector as a vector in as a point in high dimensional space, this corresponds to shifting it to a different position, basically. And what we did to control if any shifting of the same magnitude can equally alter the performance of the network, or if there's something special about the directions of the auxiliary variables, we created random perturbations, which are done by shuffling the values in the perturbed vector. So this corresponds to basically shifting the network in a random direction, as opposed to the direction of changing the auxiliary variable.
We know it's 12 minutes.
Sure, I'm almost done.
Okay, cool.
So this corresponds to, so this way we can measure the functional relevance as the difference between the random perturbation and the actual perturbation as a ratio of the original performance. And this is what we get. So we do have above zero functional relevance for almost all layers, with some difference between different auxiliary variables. For example, we can see that the spatial location is particularly important, especially in input here. We can see that information about category is sent to both C1 and C2. And we can see that in the fully connected layer, we don't, there's not much of a role of recurrent connections. So to visualize, this is the killer figure of the presentation. So since we also had connections back to the input, we can visualize what the network was doing to the input, and it looks something like this. So basically, the network is taking this very cluttered image and it's filtering out the noise. So this is the modulated input as seen by the network, and it's iteratively doing so in time so that the real digit sticks out more. So to summarize, the recurrent connections in a RNN trained for object categorization have information about category-orthogonal auxiliary variables and use them to filter the relevant information at all layers throughout the network. And both encoding of category and auxiliary variables is iteratively improved over time, which nicely relates to some theoretical perspectives arguing that a good solution for object categorization is not just to discard all information about anything other than category, but actually to make that information more explicit so as to optimally separate different object categories. And maybe this could be seen as a general framework for classification in deep neural networks, because of course, a deep feed-forward neural network is the same as an unrolled RNN. And the recurrence could just be a useful inductive bias to get to this. Thank you very much. I'm looking forward to the questions.